Hi everyone, in this video I have set aside some kinematic equation practice problems. These are 12 problems I actually wrote many years ago. They're still perfectly good problems and I change the numbers up every now and then. But in this video all I'm going to do is I'm going to show you the problem statements. I encourage you, in fact I urge you, to practice all of them on your own. Try to solve each one of them without looking ahead to the next video in which I'll have the solutions. So let's look at the problem statements. In the problems below, use the table I introduced in the video on kinematic equations, so the previous video, and decide which equation is most pertinent to the question, and only after you have done so, solve the problem at hand. It is easiest to determine which equation you should use when you consider what information you are given, as well as what information you are asked for. Only one best equation should apply in each case. Concentrate on the variables t, x, v, and a in particular, since you will be given two of them and asked to solve for a third. You should only need one equation per problem. Even though you should always have them close at hand, I highly recommend you memorize the equations featured in the table. And as I kind of hinted to in the previous video, you only need to remember two kinematic equations, and then if you're good with your algebra, you can always derive the other two. But you have to not make any algebraic mistakes. Much of this paragraph is basically just telling you that each of these problems involves one kinematic equation, and if you're very careful with how you choose it, you will be able to solve any of these problems using just one kinematic equation, as opposed to two. When I was first taking physics, I often used two kinematic equations in solving a problem, and I kind of regret that. You can cut down on a lot of your arithmetic and algebra by just doing these problems in one step. Okay, so problem one, a particle begins with its motion with velocity v naught equals v at time 0. V naught equals 5 meters per second at t equals 0 seconds. So I'm trying to be very clear about time being 0 seconds when corresponding to v naught. By t equals 3 seconds, it has reached a velocity of v equals negative 7 meters per second. Find its acceleration, assuming it is constant. Okay. So every one of these problem statements will involve constant acceleration somehow. A billiard ball rolls with constant acceleration of 4 meters per second, so 4 meters per second squared, such that its initial, corresponding to t equals 0 seconds, velocity is v naught equals negative 2 meters per second, such that its initial velocity is v naught equals negative 2 meters per second. At some later time, it is observed to have velocity v of t equals 6 meters per second. Find the time t at which that observation was made. Problem 3. A box slides with constant acceleration down a ramp. It began at position x naught equals 6.3 meters and was given a push such that v naught equals 2 meters per second. If the box is then found at x equals 16.8 meters when t equals 3 seconds, find the box's acceleration. And problem 4. A meteoroid falls straight down, constantly accelerating over a distant planet. Its height above the ground is initially, remember, t equals 0 hours, so whenever I say initial, it means t equals 0 hours. Its height above the ground is initially y naught equals 800 miles, and its velocity at that time is negative 40 miles per hour, and the negative sign indicates that the meteoroid is headed down. Find its height above the planet at t equals 4 hours, if its velocity at that time is negative 70 miles per hour. Problem 5. A cart with a fan attached to it rolls up a ramp such that its acceleration is a equals negative 4 meters per second squared and is constant. If the cart began its trajectory with initial speed v naught equals 6 meters per second and its initial position was x naught equals 3 meters, determine when it will be found at x equals negative 5 meters. So find the time is what it's asking for. And I have a hint here. Because I am looking for a later time, the solution to this problem is positive. Do remember the quadratic formula. Okay, I'll just tell you, you will at some point take a square root, and it will technically be ambiguous as to whether you will take the positive or negative square root. But according to this hint and the way that I've written the problem statement, you're going to take the positive square root. Okay, and you probably are going to need the quadratic formula. You may not. Question 6. A bubble rises up from the seafloor with constant acceleration, a equals 2 meters per second squared. Its initial height is y naught equals 5 meters, and its initial velocity is v naught equals 3 meters per second upward. At some later time, it is observed at height y equals 7 meters per second. What is its velocity at that time? And another hint, I specified that the acceleration is positive, and it is at a later time. And so your answer should be positive. Again, you will at some point have a square root. You could take the negative square root if you wanted, but it wouldn't correspond to what's being asked in the problem statement. Question 7. A race car accelerates over the starting line of a straight track at a constant rate of a equals 8 meters per second squared. Its velocity is initially v naught equals 11 meters per second, and at some later time it is observed to be traveling at a velocity of 13 meters per second. V equals 13 meters per second. Assuming the initial position of the car is at x naught equals 17 meters, find the position when it is traveling at v equals 13 meters per second. Question 8. An elevator ascends a building with constant acceleration. If its initial height is y naught equals 7 meters and its initial speed is v naught equals 3 meters per second, find its speed at time t equals 3 seconds if its height is y equals 19 meters at that time. Question 9. A roadrunner dashes across the street with a constant acceleration of a equals 6 meters per second squared. Its initial velocity is v naught equals 4 meters per second, and its initial position is x naught equals 12 meters. Find its position at t equals 5 seconds. Question 10. A swimmer accelerates at a constant rate shortly after she leaves the starting platform. Her initial position is x naught equals 5 meters, and her initial velocity is v naught equals 3 meters per second. At some later time, her position is x of t equals 8 meters, and her velocity at that time is v of t equals 9 meters per second. What time was this? Question 11. An echidna waddles along with a constant acceleration, a equals negative 0.75 meters per second squared. It initially has a velocity of v naught equals 1 meter per second. What is its velocity after t equals 8 seconds? And then question 12. A student at height y naught equals 3 meters crumples up a frustrating physics assignment and hurls it downward at the lecturer who assigned it. The initial velocity of the paper is v naught equals negative 4 meters per second, and if the lecturer stands at a height of y equals 2 meters and the paper hits him traveling with velocity v equals negative 6 meters per second, find the paper's acceleration assuming it is constant. Okay, so 12 good kinematic equation problems. Each of them requires just one kinematic equation to solve. I encourage you to solve them all before moving on to the next video. In fact, I do more than encourage you. I urge you to give it your best shot. Check your work with the next video, or use the next video if you've absolutely thrown everything that you can at each problem and can't go any further and you need a hint. But really do your best to do these problems on your own. Also, just one thing to think about why there are 12 of these and see if you can figure out how I constructed these problems. I'll tell you that if I were to try to add a 13th problem, it probably would be pretty much redundant with one of the existing problems. So try and figure out why that is, and I'll tell you why in the next video. But look at all of that, do your best, and I will see you in the next video with the solutions to these problems. All right, bye-bye.